When feeding a 600 amp panel board from a main switch using parallel 350 mcm feeders running approximately 100 feet across a rooftop, several special calculations must be taken into consideration. These calculations primarily revolve around voltage drop, ampacity derating for parallel conductors, inductive reactance, and other environmental factors that can impact the performance and safety of the installation. Let's examine the key calculations and considerations involved. Firstly, voltage drop calculations are critical to ensure that the voltage at the panel board is within acceptable limits. Excessive voltage drop can lead to equipment malfunction, reduced efficiency, and potential damage to connected loads. The process involves several steps. 1. Calculate the total impedance of the conductors. Impedance C is a measure of the total opposition to current flow in an alternating current circuit, encompassing both resistance and reactance. It's calculated using the formula Z equals R plus JX, where Z is the impedance, R is the resistance, J is the imaginary unit, and X is the reactance. This formula considers both the resistive and reactive components of the circuit. 2. Calculate the voltage drop itself. The voltage drop V drop is calculated using Ohm's law, but adapted for alternating current circuits where impedance plays a role. The formula is V drop equals I times Z, where V drop is the voltage drop, I is the current, and Z is the total impedance. This calculation provides an estimate of the voltage reduction along the conductors due to the current flow and impedance. Secondly, ampacity derating for parallel feeders is essential because the ampacity of conductors is affected when they are run in parallel. The National Electrical Code (NEC) provides guidelines for adjusting ampacity based on the installation conditions. Here's how to approach this. Calculate the adjusted ampacity by derating the ampacity based on the number of parallel conductors. Refer to NEC Table 310.15b3 for derating factors. This table provides derating factors based on the number of current carrying conductors in a raceway or cable. Thirdly, inductive reactance is a factor that becomes significant with alternating current circuits, especially when conductors are spaced apart or run in parallel. Inductive reactance X is the opposition to the change of current flow in an alternating current circuit caused by the inductance of the conductors. It's frequency dependent and becomes more significant at higher frequencies or with longer conductor runs. Calculate the inductive reactance of the conductors using the formula X equals 2 times pi times F times L, where X is the inductive reactance, F is the frequency, typically 60 Hz in the United States, and L is the inductance. This calculation helps in determining the impact of inductance on the overall impedance and voltage drop in the circuit. Now let's consider additional factors. 1. Ambient temperature. Adjust the ampacity of the feeders based on the expected ambient temperature. High temperatures reduce the current carrying capacity of conductors. Consult NEC Table 310.15b2 for ampacity correction factors based on ambient temperature. 2. Conductor elevation. Derate the ampacity for feeders installed above ground level, especially in hot environments. Elevated installations are typically exposed to higher ambient temperatures, which can further reduce the conductor's ampacity. Consider the specific environmental conditions when determining the appropriate derating factor. 3. Overcurrent protection. Select overcurrent protection devices that are properly rated for the feeder capacity, voltage drop, and fault current. Overcurrent protection devices, such as circuit breakers or fuses, are essential for protecting conductors and equipment from overloads and short circuits. Ensure that the selected devices are rated appropriately for the calculated feeder capacity, voltage drop considerations, and available fault current. Here are some recommended practices. Firstly, use copper conductors. They have lower resistance and inductive reactance than aluminum conductors, resulting in better performance and reduced voltage drop. Copper conductors are generally preferred for critical applications or where voltage drop is a concern due to their superior conductivity. Secondly, run feeders side by side to minimize the distance between parallel feeders to reduce inductive reactance. Keeping the conductors close together reduces the loop inductance, which in turn reduces inductive reactance. Thirdly, bond neutral and ground conductors to ensure proper grounding and bonding to minimize voltage drop and potential interference. Proper grounding and bonding practices are essential for safety and to minimize voltage drop and noise in electrical systems. Now let's discuss some additional points to consider. When installing parallel feeder conductors, it is crucial to ensure that each conductor is of the same length, material, insulation type, and termination method. Differences in these factors can lead to unequal current sharing among the conductors, potentially overloading one or more conductors and causing premature failure. Therefore, carefully select and install the conductors to maintain uniformity. The physical arrangement of the parallel conductors can also impact the overall performance of the system. Ideally, the conductors should be arranged in close proximity to each other to minimize the loop inductance. One common practice is to bundle the conductors together using cable ties or straps, ensuring that they are tightly packed and run parallel to each other along the entire length of the run. In addition to the calculations mentioned earlier, it is also essential to consider the available fault current at the panel board location. The fault current is the maximum current that can flow in the event of a short circuit, and it is crucial for selecting overcurrent protection devices with adequate interrupting capacity. Perform a fault current study to determine the available fault current at the panel board and ensure that the selected circuit breakers or fuses are rated to interrupt that level of current. Another important consideration is the coordination of overcurrent protection devices throughout the electrical system. Selective coordination ensures that only the overcurrent protection device closest to the fault opens, minimizing disruption to the rest of the system. This requires careful selection and setting of overcurrent protection devices based on their time current characteristics. Consider the use of ground fault protection equipment to detect and interrupt ground faults, which can pose a significant safety hazard. Ground fault protection devices, such as ground fault circuit interrupters GFCIs or ground fault relays, can detect even small ground faults and quickly de-energize the circuit, preventing electrical shock and reducing the risk of fire. Regularly inspect and maintain the electrical system to ensure that all components are in good working order and that connections are tight and secure. Loose connections can cause increased resistance, leading to voltage drop and overheating, while damaged conductors or insulation can create safety hazards. Perform periodic infrared scans to detect hot spots, which can indicate loose connections or overloaded conductors. Keep detailed records of all calculations, design decisions, and installation details for future reference. This documentation can be invaluable for troubleshooting, maintenance, and future modifications to the electrical system. It is also essential to comply with all applicable codes and standards, including the National Electrical Code, NEC, and local electrical codes. These codes provide detailed requirements for the installation and operation of electrical systems, ensuring safety and reliability. Failure to comply with these codes can result in fines, penalties, and potential safety hazards. Always prioritize safety when working with electrical systems. Wear appropriate personal protective equipment (PPE) such as safety glasses, gloves, and insulated tools, and follow lockout/tagout procedures to de-energize circuits before working on them. If you are not qualified to perform electrical work, consult a qualified electrician for assistance. Remember that electrical systems can be complex and dangerous, and it is always best to err on the side of caution. Before commencing the installation of the parallel feeder conductors, carefully plan the routing and support of the conductors to ensure that they are properly protected and supported. Avoid running the conductors in areas where they may be exposed to physical damage, moisture, or excessive heat. Use appropriate cable trays, conduits, or other support structures to protect and support the conductors along their entire length. When terminating the parallel feeder conductors at the panel board and main switch, ensure that the connections are clean, tight, and properly torqued. Use appropriate connectors and lugs that are specifically designed for use with the type and size of conductors being used. Follow the manufacturer's instructions for installation and torque specifications to ensure a reliable and safe connection. After completing the installation of the parallel feeder conductors, thoroughly test and inspect the system to verify that it is functioning properly. Use a multimeter or other testing equipment to measure voltage, current, and resistance at various points in the system to ensure that they are within acceptable limits. Check for any signs of overheating, loose connections, or other potential problems. In addition to the technical aspects of the installation, it is also important to consider the aesthetic appearance of the finished product. Strive to create a neat and professional-looking installation that is free of clutter and unsightly wiring. Use cable ties, straps, or other means to organize and conceal the conductors, and ensure that all components are properly labeled and identified. Good housekeeping practices not only improve the appearance of the installation, but also make it easier to maintain and troubleshoot in the future. Effective communication and coordination with other trades and stakeholders are essential for a successful installation. Coordinate with architects, engineers, and other contractors to ensure that the electrical system is properly integrated into the overall building design and that all necessary permits and approvals are obtained. Communicate regularly with the owner or client to keep them informed of the progress of the installation and to address any questions or concerns that they may have. When selecting overcurrent protection devices, consider the available short-circuit current rating of the devices. The short-circuit current rating is the maximum amount of current that the device can safely interrupt without being damaged. Ensure that the selected devices have a short-circuit current rating that is equal to or greater than the available fault current at the point of installation. Failure to do so can result in catastrophic failure of the overcurrent protection device in the event of a short circuit. In addition to the ampacity derating factor specified in an EC Table 310.15b3, there may be other factors that can affect the ampacity of the conductors. For example, if the conductors are installed in a thermal insulation, their ampacity may need to be further derated to prevent overheating. Consult the NEC and other relevant standards for guidance on derating conductors in specific installation conditions. When running parallel conductors, it is important to ensure that each conductor is properly identified and labeled. Use color-coded tape, labels, or other means to identify each conductor and its corresponding phase or neutral connection. This will help to prevent confusion and errors during installation and maintenance. In addition to the voltage drop calculations mentioned earlier, it is also important to consider the voltage regulation of the electrical system. Voltage regulation is the change in voltage from no load to full load conditions. Excessive voltage regulation can cause problems with sensitive electronic equipment and other loads. Design the electrical system to minimize voltage regulation and ensure that the voltage remains within acceptable limits under all operating conditions. Regular maintenance and testing of the electrical system are essential for ensuring its continued reliability and safety. Perform periodic inspections to check for loose connections, damaged conductors, and other potential problems. Test the overcurrent protection devices to verify that they are functioning properly and that they are set to the correct trip settings. Keep detailed records of all maintenance and testing activities. If any problems are detected during maintenance or testing, take prompt corrective action to repair or replace the affected components. Do not delay repairs, as even minor problems can quickly escalate into more serious issues. In addition to the technical aspects of the electrical system, it is also important to consider the environmental impact of the installation. Use energy-efficient equipment and materials whenever possible to reduce the environmental footprint of the electrical system. Properly dispose of any waste materials generated during the installation in accordance with local regulations. Consider the use of renewable energy sources, such as solar power, to further reduce the environmental impact of the electrical system. Finally, remember that electrical work can be dangerous and should only be performed by qualified individuals. If you are not qualified to perform electrical work, consult a licensed electrician for assistance. Do not attempt to perform electrical work yourself, as this can put yourself and others at risk of injury or death. In addition to the copper conductors mentioned earlier, aluminum conductors are also commonly used in electrical systems. Aluminum conductors are less expensive than copper conductors, but they have a lower conductivity and are more susceptible to corrosion. When using aluminum conductors, it is important to use appropriate connectors and lugs that are specifically designed for use with aluminum conductors. These connectors and lugs are typically made of aluminum or a bimetallic material to prevent galvanic corrosion. When terminating aluminum conductors, it is important to clean the conductors thoroughly and apply an antioxidant compound to the connection before tightening the connector. This will help to prevent corrosion and ensure a reliable connection. In addition to the overcurrent protection devices mentioned earlier, surge protection devices (SPD) are also commonly used in electrical systems to protect sensitive electronic equipment from voltage surges and spikes. SPD are typically installed at the service entrance and at downstream panel boards to provide comprehensive surge protection. Select SPD with an appropriate surge current rating for the application and install them in accordance with the manufacturer's instructions. Grounding is a critical aspect of electrical safety. A properly grounded electrical system provides a low impedance path for fault current to flow back to the source, which helps to trip overcurrent protection devices and prevent electrical shock. Ensure that the grounding system is properly installed and tested in accordance with the NEC and other applicable standards. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can cause electrical shock. Ensure that all metal parts of the electrical system are properly bonded together in accordance with the NEC and other applicable standards. Electrical noise can cause problems with sensitive electronic equipment. Electrical noise can be generated by a variety of sources, including motors, transformers, and electronic devices. Shielded cables, filters, and other noise reduction techniques can be used to minimize electrical noise in electrical systems. Harmonics are another potential problem in electrical systems. Harmonics are voltage or current waveforms that are multiples of the fundamental frequency. Harmonics can be generated by nonlinear loads such as electronic devices and adjustable speed drives. Harmonics can cause problems with equipment overheating, voltage distortion, and reduced power factor. Harmonic filters and other mitigation techniques can be used to reduce harmonics in electrical systems. Power factor is a measure of how efficiently electrical power is being used. A low power factor can result in increased energy costs and reduced system capacity. Power factor correction capacitors can be used to improve the power factor of electrical systems. The National Electrical Code (NEC) is a comprehensive set of standards for the safe installation of electrical systems. The NEC is updated every 3 years and is adopted by most states and municipalities in the United States. Ensure that you are familiar with the requirements of the NEC and that you comply with all applicable codes and standards when installing electrical systems. Continuing education is essential for electrical professionals. The electrical industry is constantly evolving, and it is important to stay up to date on the latest technologies and best practices. Attend training courses, read industry publications, and participate in professional organizations to stay informed about the latest developments in the electrical industry. Contact a qualified electrician for accurate calculations and proper installation. Failure to consider these special calculations can lead to inadequate power supply, voltage drop issues, and potential safety hazards.